The camera is rolling. So
Okay. A very good morning, ladies and gentlemen, and potential aerospace materials engineers of Malaysia. This is our first lecture on aerospace materials. What are the special requirements of aerospace materials? They should be lightweight, strong, withstand the temperature from minus 43 degrees Celsius to plus 43 degrees Celsius when they are landing in tropical country. So the normal materials are aluminum and its alloys, titanium to withstand the high temperature in the gas turbine up to 1000 degrees Celsius, and its alloys, superalloys, which are made of more than 4 different elements, polymers, rubber, steel, metal matrix, composite material. These are the intelligent materials. They remember the memory where they are subjected loads of high temperature, high stress. Polymer, matrix, composite. What are the special requirements or properties of these aerospace materials when you want to send some aircraft to moon or spacecraft? Now, aerospace structural applications frequently require strength better than the normal material we use for buildings and the cars and tables and chairs. They must be very, very light, must be very stiff and fatigue resistant because they are subjected to cyclic variation from 1 million cycles to about 10 million cycles. So they should be able to withstand fatigue stresses. Engine components of aircraft require materials with good creep strength. Why creep? Because subjected to very long period of duration, the load and causes creep. And microstructural ability at very high temperatures at around 1000 degrees Celsius. Many composite materials are stronger than steel like fiber, reinforced plastics, lighter than aluminum and stiffer than titanium. Titanium is the stiffest material available on the earth. Hence the use of advanced composite materials in aircraft construction has formed 2% in 1972 to over 30% today. We are using advanced composite materials, non-steel and non-alloy in recent days. Figure below, which I will show here in a few minutes, shows the comparative strain weight ratio of various aerospace materials to function. Okay. For the different temperatures and stresses. Modern aircraft, if you see Airbus from London to Australia with 490 passengers, they had a failure, a disaster in Indonesia. One engine cover fell down. It's because of the fatigue, creep and the bad design. The material was very good. So what are these eventualities which come on the modern aircraft carrying huge number of passengers, fuel which is combustible? The requirements are, which I have showed again in the figure very soon. Looking at the future, maybe 2015 to 2020, we may have 1,000 passenger carrying aircraft from London to New York, London to Melbourne and so on through Kuala Lumpur of course. So looking at these, the material requirement of advanced hypersonic structure such as X-30 NASP include both tensile as well as creep strength, should be very, very high. Such a plane that can take off from runway like Kuala Lumpur International Airport and fly directly into space beyond the Earth's atmosphere and reaching a speed in excess of 20 times the speed of sound. The present Mach number is only about 1, even supersonic aircraft about 2. Now we want Mach number, that's the speed of the plane to the speed of sound in air, 25 times the speed of sound would involve high temperatures, very, very high temperature in its structure. The maximum temperature at leading edge of the body will be near 1500 degrees Celsius, which is equivalent to 2700 degrees Fahrenheit. Radically, different aerospace materials will be required to provide properties of high strength, lightweight, very lightweight, lighter than even water, and stability at very high temperatures. Aluminum copper alloy has been found very suitable, though copper is very expensive and the efforts are being done to reduce the cost. The aluminum copper alloy, first used in structural member of aerospace during the First World War, 1914 or so, was beryllium, which is still used for utensils in many countries, contained 4% copper, 0.5% magnesium, 0.5% silica, 0.7% iron and ferrous, and 0.7% manganese to give the strength. The main function of manganese being was to refine the grain size of the structure. The most metallurgical important feature of aluminum alloy is the ability to improve mechanical properties when suitably heat treated. You can increase the properties of aluminum considerably by proper heat treatment, T1, T2, T3, T4 and so on. Aluminum copper alloy for aerospace application are usually given a special heat treatment called age hardening. With age time also it becomes harder. Age hardening of copper aluminum alloys. Age hardening of aluminum copper alloy containing 4% copper involves the following steps. There are 4 steps involved. Heating to a temperature of 550 degrees Celsius and then cooling very, very slowly. You leave in air, it will slowly cool. But if you put a drop, it will cool very suddenly, which is not allowed. Very slowly to room temperature, about 27 degrees Celsius. Reheating. Then after cooling again, reheat the alloy to about 550 degrees centigrade and then water quenching, put in water. This makes the alloy very strong. Number 3, allowing the alloy to remain at room temperature for about 6 days. See that heat treatment, how difficult it is. 6 days remain at the room temperature, so strength and hardness increases. Last step, an improvement in properties over those obtained by ordinary natural age hardening can be obtained by tempering the quenched alloy at about 200 degrees Celsius for a very short period. This process is called precipitation hardening. It's a special name. So this makes the alloy very suitable for aerospace application. Now what is the metallurgical effect on this? So metallurgy of age hardening and precipitation hardening. Let us assume that we have an aluminum copper alloy containing 4% copper at temperature above 550 degrees Celsius. This will consist entirely of an alpha solid. This is a phase in the alloy. We have liquid phase, liquid solid phase and solid phase, as indicated by the diagram which I will present together in the equilibrium diagram. If we now allow the alloy to cool to room temperature, the equilibrium will be reached at each stage and the particle of the intermetallic compound copper aluminum oxide will form a non-coherent precipitate. This precipitation will show commence at A, which is shown in the diagram, and continue until room temperature. Only for 0.2% of the copper remains in aluminum solution stage, remaining in the solid stage. The resulting structure will lack strength. It will not have the enough strength which we need because only 0.2% copper is left in solution. Remaining has been dissolved. And it will be brittle because of presence of coarse particles of copper aluminum. This brittleness, that if you bend it, it will break. It will not be flexible. If the alloy is now slowly reheated, the particles of copper aluminum will be gradually absorbed until at a point shown in the diagram, we once more have a complete solid solution of alpha. On quenching the alloy, we retain the copper in solution and in fact produce a supersaturated solution of copper in aluminum at room temperature. In this condition, the alloy is somewhat stronger and harder because there is more copper actually in aluminum, and it is also much more ductile. Ductile means if you bend now, it will not break, it will just deform because the brittle particles of copper aluminum are now absent. If the quenched alloy is allowed to remain at room temperature, it is found the strength and hardness gradually increase, and we need harder material and the strength also, and reaches a maximum in about 6 days. So for 6 days you have to keep the alloy in that condition. The completely alpha phase structure obtained by quenching is not the equilibrium structure at room temperature. It is in fact supersaturated with copper, so copper atoms diffuse out according to the following equation, which also I'll show you. Copper plus 2 aluminum atoms, which gives the intermediate current precipitation. Okay. Thank you very much for today's lecture. We'll recap this in the next lecture and continue with the further material for aerospace. Thank you very much for attention.